Hi, once again, let's start the session. So in the previous lecture, we were talking about the binary number system. So for our ALU design, the most important part is to know more about the number representation. So in today's lecture, we try to discuss the two's complement and floating point arithmetic numbers. So two's complement is used. Why this two's complement is required in the computer arithmetic that we discuss. So in the number inside your computers, we can find that the numbers either having a zero or one. So zero means it is uncharged transistor, and one means it is a charged transistor. So all numbers are represented in the form of zeros and ones, so that these can be given as an input to your transistors, which build off of your gates, as we discussed, and it will give the output based on the gate performance or gate's functionality. So the numbers which we have seen till now, in the previous discussion, we have taken the decimal numbers, are the integer, positive integer numbers like 25, 26, and something like that. So we call those numbers as your unsigned positive integers. So they represented with the bits corresponding to their binary representation. Like, if you have number 2, so that is the unsigned number, it can be represented in the binary form as your 1, 0. The binary form, by just doing, by dividing this with the 2, you will get the 1 and remainder will be 0. So you will get the 1, 0 as your the representation of 2. So if you take 3, suppose, then it will be represented as 1, 1 in the binary form. So any unsigned positive numbers are there, they are equivalent to their binary representations. But along with that, if you have any negative integers, suppose, so -3, something like that, so they are represented using a format which is slightly different from its absolute value in the binary. So there are no negative signs in the transistor. So negative sign is also represented with its some digits. So to represent these negative values, we use the separate the mechanism we call the two's complement encoding. Two's complement encoding. So in this two's complement encoding, how it will be used to represent the signed numbers that we will discuss. So, how to represent the signed numbers. Signed numbers means the positive integers may be positive integers represent like plus, suppose A, where A is any number that starts from your, 0 to, some n digits. And negative numbers will be represented with like, minus A, that will also start from your 0 to n numbers, suppose. So if any number which is represented with plus or minus, we call them as your signed numbers, signed number representation. So plus and minus sign is used for any decimal numbers. So we call them as your signed numbers. So these signed numbers can be represented in 3 different ways. Okay. So the signed numbers can be represented in 3 different ways in the signed binary number representation. One is signed magnitude representation. Another one is one's complement, and another one is two's complement. So in the first one, in signed magnitude 1, any number, the leftmost bit of any binary number that indicates the sign, like, if you have any digits like 10001, the leftmost bit represents the sign and remaining bits represent as your magnitude. So if you take any number, first bit represents, the leftmost bit indicates the sign, and remaining bits indicates the magnitude. So we call this as your signed magnitude representation, binary representation of any number. So The positive numbers represent with the 0 bit and negative numbers represent with 1 bit. Okay, positive represent with 0 and negative represent with 1 bit. So suppose if we have a number like 12, the 12 is the positive number. So the binary equivalent of your 12 can be represented as, if you do do the operation of 12 divided by 2, the quotient is 6 and the remainder is 0 here. Then 6 will be divided by 2 and it will give the quotient is 3 and the result is 0, remainder is 0. Then 3 divided by 2, the quotient is 1 and remainder is 1. So then 1 divided by 2, the quotient is it is about 0. So it will give the remainder will be 1 here. So if you write this number in a different way, in a reverse order, then it will give you the 1100. But if you take any register, if that register size is, if the register size is, suppose 8-bit register, then the register will be filled with 8 bits, filled with 8 bits. So the 12 is represented as 1100. So remaining bits represented, filled with zeros, and the leftmost significant bit filled with your 0, because 12 is a positive number. If you have a minus 12 number is there, so the binary, the signed binary representation of this minus 12 is the leftmost bit is 1 and the minus is represented with 1 and the actual the 12's binary representation is 0001100. So this is the first way of representation of signed binary number representation. Second one is ones complement. This is very important. So in the ones complement of any binary number, that involves inverting all the bits. Suppose the ones complement of a given number, binary number, suppose 00110011, then the ones complement of this signed number, the ones complement of this signed number is every bit is inverted into every bit is inverted into its opposite bit. Like 0 become 1, 0 become 1, 1 becomes 0, 1 becomes 0, 0 become 1, this 0 become 1, this 0 become, this 1 becomes 0, this 1 becomes 0. So that is the every bit is inverted. So that gives the ones complement. So in this case, we have 8 bits are there. So we call these 8 bits, for this ones complement, the generalized formula which will be given here as there will be n bits and the number of that n bit is this number. This is the number, in that there will be 8 bits are there. Okay. Similarly, so for any n bit numbers, the ones complement is written as 2 to the power of n minus 1 minus that numbers. That means if we have this number, then 2 to the power of, here n is equal to 8. So 2 to the power of 8 minus 1, from there you can subtract this number, that will give the ones complement. So when you subtract this number, you will get the ones complement. So here this is called the diminished radix complement, complement by the mono, since the ones complement for the base of your radix 2. So to find the negative of ones complement number, it take the ones complement. So that is for the positive number of your 1, the signed representation is signed magnitude representation is, that is what we have seen in the previous case, that is 0, 1, 1, 1, 1. It is a positive number. So there is no change in the signed magnitude representation of the binary representation for the ones complement as well as for your signed magnitude. But if it is a negative number, if it is a negative number, then the sign bit will be 1 and all the remaining bits will be complemented, ones complement. So it 0 become 1, 0 become 1, 0 become 1, 1 becomes 0, 1 becomes 0, and 1, 1. So that will be the ones complement of your negative number. For positive number, there is no difference between your signed magnitude representation and ones complement representation. So the positive numbers are equivalent. Yes. For ones complement, yes, you are correct, Molana. To represent negative numbers, your signed magnitude also represent negative number. Your ones complement also represent negative number. The only difference is in signed the negative number representation in ones complement is sign bit kept as 1 and remaining bits of your actual 12 value is inverted. 12 value bits are inverted from zeros to 1. So this magnitude bits are inverted so that it will represent minus 12. Okay. So then comes to your 2's complement. 2's complement representation of the number. So the 2's complement of binary number that involves inverting all bits plus adding 1 to the inverted bits. Adding 1 to the inverted bits. So suppose the 2's complement of this number, that is n, having n digits, suppose n bits, okay, is equivalent to, first of all, it will be inverted. Zeros invert into 1, 0 invert into 1, 1, your 1 invert into 0, 1 invert into 0. This is 1, 1, 0, 0, 1, 1, 0, 0. And whatever the result is there, so here it will do the 1, 1, 0, 0, 1, 1, 0, 0, and it add 1 bit to this. The one's complement plus 1 gives the 2's complement. When you add this, you will find 1, 0, 1, 1, 0, 0, 1, 1. So this is the 2's complement of your given number. So for any n-bit register, if n bit of your number n is there, then the 2's complement will be written as 1's complement plus 1. 1's complement plus 1. So it will give the 2 to the power of n minus 1 plus 1. So if you simplify this, you will get that the 2's complement formula is 2 to the power of n minus n is the 2's complement of any number. 2's complement of any number. So how it will be represent the positive, if it is a signed positive number, then signed positive number follows the signed magnitude and your one's complement and 2's complement. The 2's complement all are same for any positive numbers. But for negative numbers, the first leftmost bit kept the 1 to represent minus, and whatever the positive value is there, that positive values 2's complement will be taken. 2's complement will be taken. So what is the 2's complement? First it goes through the 1's complement of this. So 1's complement of your 12 becomes the 1, 1, 1, 0, 0, 1, 1. Then it will be adding plus 1 to, so it becomes your 2's complement. So you will get 1 plus 1 is 0. Here is carry. So 1 plus 1 is 2. That is 0 here, 1 is carry here. Then you will find 1, 0, 1, 1, 1. And the last bit is your negative bit. So that is the 2's complement of your 12. Okay. So from here, we can see this, that two different ways of doing this 2's complement One is simply complement each bit and then add to the result is one way. That is what we have seen now. For any number, do the ones complement of that and then add that. So it will give the twos complement. Another way is starting with the least significant bit and copy all the bits up to the including first one bit, then complement the remaining bits. That means what? If a number is given to us, so then you start scanning from your least significant bit to your most significant bit. And as soon as you encounter the one, suppose, okay, then all the remaining bits will be inverted. So, until suppose after this number, if you have zeros, for example, if zeros are there, then you start scanning from left to right, from least significant bit to right. So, if any bits are there here, suppose 1, 1, they will remain same. But when it encounters the first one, that will keep as it is, and all the remaining bits from that will be inverted. That will give also the twos complement of your number is another way of representation. One way is first do the complement of each bit and then add one to it, or else you can start scanning from left to right and if you encounter any one bit and keep that bit as it is, and after that all the bits will be inverted is another way of twos complement. So let us see some other examples also. Using ones complement number, adding numbers is easy as said. So suppose if you have two numbers like the binary numbers 1100 and another one is 0001. So they are represented with plus. So they are the signed positive numbers. Signed positive numbers, if you compute that in decimal, suppose it will give you the value 12 and this give the value 1 in decimal part. So they are represented with plus 12 and your plus 1. So plus 12 can be represented as your plus 12 in the binary form is this. So you are adding plus, so plus will be added represented with 0, so 0 will be added on leftmost side. For 1 also 0 will be added on leftmost side, and after that you can add these two numbers. The signed positive numbers will give you the result. So in this, what happens when you are adding the signed positive numbers, 12 and 1 signed positive numbers, you will get the carry bit. In some example, you will get the carry bit. When you will get the carry bit to design your ALU, that carry bit will be again, add this carry bit to the lower order bit of this result. So it will give the final result of two signed bit positive numbers. So in this example, when you are adding this, suppose, then if you get any number, and if you get any carry bit here, so that carry bit will be added to the lowest bit in this. So that will give the final result. So this will help to design the arithmetic and logic unit, the ones complement addition. If there is no carry bit, then this will become the final result. If there is a carry bit, then that carry will be added here, and that will give the final result. Am I clear, Mulano? When you are adding any two positive binary numbers, when you are adding two positive signed binary numbers, during addition, if you find any carry bit, that carry bit will add to the lower order bit, so will generate the final result. For example, let us see this. Suppose 0, 1, 1, 1, 0, 1, 0, 1. If you add this, what happens? 1 plus 1 is 2. So that is 0 here, carry is here. 1 plus 1 is 2 plus 0 is 2. 0 here, 1 here. 1 plus 1 is 2, 2 plus 1 is 3, so 1 here, 1 will be here. So 1 plus 0 is 0, 0 plus 1 is 1, sorry, 1. So you will get this. So if the two numbers are same, then you will get this result. So this will be final. So you don't have any carry here. But in some cases, when you are adding the positive numbers, okay, I mean when you are adding the signed numbers, in that case you will get some the carries. What is that? If one is positive and another bit is suppose a negative, when you are adding two signed bits, like when you are adding two signed bits, okay. So when you are adding the two signed bits, two signed numbers of your one's complement, suppose, then the positive numbers will be represented as it is, as signed magnitude, by just adding 0. For negative numbers, suppose, if we're having the negative number, suppose, so that is subtract minus 1, I know this number, from this number, in that you can write that to minus 1. So minus 1 will be represented in this fashion. So in that case, you are doing the ones complement subtraction or the addition of that. So when you are adding this addition operation, when you add the 12 plus minus 1, 12 plus your minus 1, when you are adding this, you will get the carry bit. So when you are having this carry bit, that will be added, so it will give you the final result. If both the numbers are positive, that is 12 plus your 1, that's as usual the similar operation of your decimal. But when you are doing this is also signed number, this is also signed number, and asking you to do the subtraction, then in that case you will get the carry. So that carry will be added at the lower set part in one's complement. Similarly, in two's complement, it is slightly different. In two's complement, the suppose we wish to add the positive, signed number 1, binary number 1, and signed binary number, suppose 12, for adding these two, it is similar to your signed magnitude as well as one's complement and two's complement, because the positive numbers equivalent to the decimal number equivalent to the binary numbers. So the two's complement of this number is this one only as it is. There is no change in that. Two's complement of this one is also as it is. That will be added. And in that, if you find any carries, then the final result, the carry bit is ignored. If it is a two's complement subtraction operation, in the subtraction operation, you can find the subtraction operation means you are doing the negative operation. So that the subtraction operation will find the minus symbol. So for minus symbol, you have to do for positive number, its representation is decimal representation is 12, binary representation is 1100. It is a positive value plus is there, so you are adding 0 to that plus, so that gives the two's complement. For negative minus 1, so the binary representation of 1 is 001, and minus is prefixed to that. So that minus is represented with minus 1, and two's complement of this number is, it can invert all the bits into 0 and add 1 to this. So it gives the 1, 1, 1, 1. So that will be two's complement, and the minus symbol is added here. That is the negative value of that. So after that, you are going to add these two numbers. That will give you the result at 11. So by doing that operation, if you find any carries, that will be ignored in the final result. So this is another example for doing the subtracting 5 from your the positive signed number is 13. So it can be represented in the binary form as your 1101. So it is positive, so plus. So the two's complement of this number is 01101. For negative, for 5, it can be represented as your 0101. and it is -1. So this minus is converted into 1. So it becomes the 1, 1, your 0, 1, 1 by doing the ones complement of this plus 1. So then you can simply add these two numbers that will give the result. So discarding the carry bit, the sign bit is seen to be 0. So indicates a correct result. Indeed, if you do this, the what you call the 13 minus 5, you will get 8, and that will leads to the same result. Yes, for two's complement, addition or subtraction, the carry bits are ignored. That. So if you summarize this in two's complement encoding with n bits, suppose if you have this is very important for your assignment also. If two's complement encoding with the n bits, so n may be your 2 bits, n may be 3 bits, n may be 4 bits. That means if you have a number, suppose the digital numbers, decimal numbers of 1, 2, 3, 4. So if n is equal to 2 means every decimal represent with 2 bits. That is 0, 1. 2 is 1, 0. 3 is 1, 1. 4 is your 1, 0, 0. But it is not possible here. So maximum how much you will find? 2 to the power of 2 is equal to 4. That starts from 0 to your 3. If n is equal to 3 means 2 to the power of 3 is equal to 8 means you can represent up to 8 numbers. So that is, you can use 3 bits to represent any number. That is 0, 0, 1 for 1. For 2, it is 0, 1, 0. For 3, it is 0, 1, 1. For 4, it is 1, 0, 0. For 5, it is 1, 0, 1. For 6, you will write the 1, 1, 0 and so on. So if n is equal to 4, then every number represented with 4 bits, 0, 0, 1, 0, 0, 1, 0, 0, 0, your 1, 1 like that. So to the two's complement encoding of your signed numbers, it may be positive or negative, signed numbers with n bits. For positive numbers n, it is encoded with its binary representation only. That means, same, if decimal value is 2, its binary representation of this one is your 1, 0, same. If you have suppose 7, then binary representation is 1, 1, 1. There is no change in that. But if it is a negative number, minus n, it is encoded with the binary representation of 2 to the power of n. 2 to the power of n minus that number. Suppose minus 7 is there means, now how can you write if this minus 7 is represented as minus of your with 3 bits, suppose 1, 1, 1, suppose 3 bits. That means your 2 to the power of 3 it is. 3 bits is using. So that is 2 to the power of 3 minus the number is 7. So it will give you the result 1. So the what you call the 2's complement of minus 7 is your 1. So that 1 is represented in 3 bit as your 0, 0, 1. So note that for 2's complement encoding, the highest bit for a negative number is always 1. The highest bit of your negative number is always 1. So let us do this exercise so that you can understand. There are positive decimal values and negative values are there. So these are the signed values, signed decimal. Assume that there are the signed numbers are there. And the 3-bit 2's complement, if I ask you that a 3-bit 2's complement encoding for these decimal values, so then for every bit representation, you will take 3 bits. So for 1, it will be represented with 0, 0, 1 because of 3-bit 2's complement encoding. If it is asked you that 4-bit 2's complement encoding, then you need to add one more bit to this number representation. If it is suppose 5-bit 2's complement encoding, you will add one more 0 here. Am I clear up to now for 2's complement? The positive number they are equivalent to their binary representation. Okay. Yeah. So for one, in this example, a 3-bit complement, suppose, so that is 1 represented with 001. It is equivalent to its binary number. 2 is equivalent to 010, equivalent to its binary number. Okay. So here you can see the third bit is using to represent a positive sign. And for 3, it is represented as 011. So it is like represents that +3, +2, and +1, the meaning of that. Now we have the 4 is there. Any negative number is there. So 2's complement encoding of this negative number, the signed negative number. In that case, we need to use the formula that 2 to the power of n minus capital N, where capital N represents this number minus numbers. So in this case, we are asking to 3-bit 2's complement. So it becomes 2 to the power of 3 minus that number. So in 2 to the power of 3 minus number is your 4. So that is equal to your 8. 2 to the power of 3 is 8 minus 4. That is equal to 4. So 4's you can write as your 100. So in that case, the -4 is represented with the leftmost bit is negative number, and its two absolute its value, different value is your 00. So similarly for 3, you'll write 8 minus, because 2 to the power of 3 is equal to 8, and where your n is equal to the number 3 here. So you will write 2 to the power of 3 minus the capital N, that is 3, is equal to 5. It can be represented as 101. So the 2's complement of -3 is 101. Similarly, for -2, it is 8 minus 2, that is 6. It will represent it as 110. So 2's complement of -2 with 3-bit encoding is 110. 2's complement of -1 and represent in 3-bit 2's complements means 8 minus 1 is equal to your 7. That will be represented as 111. So 2's complement of -1 in 3-bit encoding is 111. Okay. So for 2's complement of any negative number, you should follow the formula that 2 to the power of n minus capital N, where this n gives small n is equal to the number of bits used to represent. Number of bits used to represent the number. Represent the number. Where capital N is a given number. So then when you fit these two in this one, then for this -4, so here 2 to the power of n, we are asking that encode all these decimal values in 3 bits. So small n is equal to 3 bits, whereas capital N in case of your 4 is, this -4 is 4. So you will write 2 to the power of 3 to fit in this formula, 2 to the power of 3 minus your 4. So that will be equal to your 8 minus 4 is equal to 4. So when you get this result, that will be converted into the binary form as your 100. That is the the 3-bit 2's complement encoding the 3-bit 2's complement encoding of your minus 4. Is it clear, Molano, now? Okay. Okay. So now, if you are still not understanding, can you please, tell me what is where you are getting the difficulties? 7 would still have the same value number. See, when 7 is having the 111, you are absolutely correct. Then 7 is positive number, right? Good. So how do you represent positive for 7? When you add 0 to the 7 values, then how many bits it becomes? Correct. So in our example, we asked for 3. So we have given example with very smaller numbers. Now I will ask the question for all of you to participate that. Please write the what the 3-bit 2's complement of 7, as he said, 7, 8, 9. Okay, not 3-bit. Use the 4-bit 2's complement for the decimal values 7, 8, 9, minus 10, minus 11, minus 12, and minus 13. Please give the answers quickly in the chat box. 4-bit 2's complement encoding of decimal values 7, 8, 9, minus 10, minus 11, minus 12, minus 13. So here every bit is represented. Let me quickly say, for 7, the positive value, it is equivalent to its binary value is 1, 1, 1, and positive value represented with 0. So it becomes 7, positive 7 now. Similarly, for 8, it will be represented as 1, 0, 0, 0. So in that case, how to represent the positive value of this? Because the leftmost bit is 1. So that is not equal to your the what you call the positive 8. So how to represent that? We need to add 0. When we need to add 0, it becomes your 5-bit 2's complement. Correct? So the 2's complement, that's why we say that for any n-bit number, we call these are n-bit numbers. N-bit numbers, and this is we call n, then we write the formula 2 to the power of n minus n. So in that case, if you have a large number, that means the number of bits in the large number will be automatically increase. Okay, so this slide is very important. Let me quickly give the 2's complement of minus 11. The number of bits depends on your choice. 2's complement of 11. I expect answers from every participant in the class. Fanning is saying that 4 1s 0 1 0 1. Mm-hmm. That's good. What about others? Okay. So you please cross-check this one, because you will get the today night I'm going to announce the assignment 2. So you will get this kind of questions in the assignment too. Okay. So let me quickly go on that. The another way of representation is, up to now we have seen the decimal, signed decimal numbers and signed binary numbers. What about the floating point numbers? In programming, we will have the floating point numbers also. So the standard format for this floating point number representation is IEEE 754 standard. So in this IEEE 754, it gives the two different standards for representing the floating number. One is single precision, the single precision, and your double precision. Single precision way of representation means represent any floating point number with 32 bits. In double precision, represent any floating point number encoding in 64 bits. That's the difference. But we are going to discuss most about the 32-bit single precision representation. So for an n-bit register, it can represent the unsigned integers in the range from your 0 to 2 to the power of n minus 1. For the n-bit register, that can represent the signed integers, that covers the negative values as well as the positive values. Okay, so in that, it will start from minus 2 to the power of n minus 1 to 2 to the power of n minus 1 range. So however, there are very large numbers and very small numbers are there. Very large numbers, for example, 3.1550 multiplied with the 10 to the power of 23, are very small numbers. For example, 10 to the power of minus 1, it gives in the minus range. It gives in the positive range of that. So the rational numbers with the repeating digits, we write that 2 by 3 as 0.666, or irrational numbers such as 2 to the power of 1 by 2 or 3 to the power of 3 by 5, like that, any irrational numbers. And the transcendental numbers such as the exponential numbers like e equal to 2.718, etc. So all of which needs to be represented in computers for the scientific computation to be supported. So we call this manipulation of these type of numbers in these ranges, we call the floating point arithmetic, because the decimal point is, you're finding the decimal point here, you're finding the decimal point here, you are finding the decimal point here. So this, because this decimal point is not fixed. For integers it is fixed, but for floating number it is not fixed. So in C language or C programming language, that such variables we call that your floating data types. So the general scientific notation for real numbers, the scientific notation for real numbers can be represented as m multiplied with 10 to the power of n for decimal scientific, the real numbers. So where your m, that can be written as your, where m is your the decimal number part. So suppose your decimal notation like simple numbers to the 300, or some decimal pointed numbers and negative decimal pointed numbers, how they are scientifically represented in the notation of your scientific notation. That means this will be represented in the real number format as 2.0 multiplied with it is a decimal, so 10 radix, and how after decimal, how many digits are there means 0, so you will write 0. So this can be written as 3 dot your 0, and these two zeros will be represented as 10 to the power of your 2. If this floating point number is there, it can be written as this dot will be shifted to your the first integer digit, after the first integer digit, and how many positions it is shifted from its current position to the next updated position will be counted as 1, 2, 3, 4. So it will be written as your 4 dot the remaining number multiplied with 10 to the power of 4. And for negative number also, it says that minus 2, the dot is shifted to the right side here. So it is represented in a negative way. Represented in a negative way. So what mean to say from this table is, in the notation of your in the scientific notation, before dot, only one integer digit will be there, or it takes only one integer digit. Okay, so that integer digit may vary from your 0 to 9. Okay, and after that it will have the fractional digit parts. So that is also the combination of your 0 to 9, that is multiplied with the 10 to the power of how many, the dots, this dot, how many positions it is moved positive. If move on positive, so it will take plus. If it is moving in right side, it will take the negative to the power of that. So from here, similarly, to your the decimal real number representation in scientific notation, the real numbers in binary format with scientific notation is similar. So before dot, it will have only one positive. That means the notation is having one. So we can express the real numbers in this scientific format, that -1. So after that, you are having two portions. After dot, you will have one portion, and this is multiplied with 2, because it is a binary format with its exponent. This exponent explains how many positions that this floating point is moved, either in positive way in the left side of that or right side of that. So this part we call the fractional part, and this part we call the exponential part of the real number, and while e is the exponential in the base 2. So the dot before the fraction part is called the binary point. So this dot we call the binary point, whereas in this case, this dot we call the decimal point, because we use the radix 10 here, right? So here we need to note that there is only one digit before this binary point. Before this binary point, there will be only one digit, and that digit is always 1. That digit is always 1. Whereas in decimal, there will be only one digit before the decimal point, and that digit is always in between your 0 to 9 combination. So since the digits in this binary, since we use the digits zeros and ones, so we can always remove the leading zeros and leaving a 1 before the decimal point. Sorry, this the decimal point in the decimal one, and binary point in this, the binary real representation. So the computer arithmetic that can support the binary real numbers in their scientific format, we call that as your floating point. Floating point. So the position of this binary point is moving, that depending on the value of your exponent. If exponent is a positive value, suppose if exponent is a positive value, that means your decimal point is positive value. Your decimal point, binary point is moving on left side. If it is a negative value, your binary point is moving in the right side. Here it is, the binary point is moving the left side. So an integer is a fixed point, as the binary point is always at the end of that integer. So in C language, we call that as your float data type. So for encoding any real numbers or floats with the bits, the standard formula that we call the IEEE 754 standard formula, that defines that it derived from this scientific notation, which we just saw. A binary floating point is uniquely identified by its sign, fraction, and exponent. So first part is your sign part. So if it is positive, will be represented with 0. So zeros will be the leading zeros of your binary decimal point will be ignored. If it is negative, then that will be kept as your sign point, followed by the notation, scientific notation. So in this scientific notation, we call this fractional part as your Montes also. Fractional part as your Montes also. So in IEEE 754 standard is having two precisions. One is your the single precision, another one is double precision. In single precision, the floating point encoding represents with the 32 bits, in 32 bits, whereas double precision represents with the 64-bit encoding. So we continue with the single precision, that is 32 bits encoding. So in that single precision, how it will be represented means the standard defined that there will be 32 bits, starts from the most significant bit to your least significant bit. And from here, you can see 0 to 31 bits. The first bit of your representation, 1 bit, represents the sign. Next 8 bits represents the exponent part, and next 23 bits represents your fractional part. So your sign represents 1 bit, your fraction represent with the 23 bits, your exponential represent with the 8 bits. So total it is the 32-bit representation. So we call this as your IEEE standard 754 single precision, your single precision of your 32-bit floating 32-bit encoding of your real numbers. So let us see this, the range of this. So 1 bit for the sign and 8 bits for the exponent and 23 bits for the fraction. So the maximum positive float values, with this 32-bit encoding lies in between 1 plus your 20, because the 23 bits for your fraction part we are using. So maximum we can use from your negative to positive value is your 1 plus your 2 to the power of minus 23, that is multiplied with 2 to the power of, the range is 127. And it is roughly that 10 to the power of 38 in decimal sign. But the maximum positive float value of your 32-bit encoding, the minimum positive float value of your 32-bit encoding is in this range, that is in between your 10 to the power of minus 3 in the range. So any number which is larger than this maximum cause will give you the overflow of bits when you are adding, the subtracting of that. And while any number which is smaller than this range will cause the underflow button. That means when you are doing the subtraction, you must borrow. So if that is smaller than the negative one, there will be an underflow there. So for a 1 bit for the for your double precision format is standard format is the IEEE 754 double precision. Your double precision takes 64-bit encoding, 64-bit encoding of your float numbers. So that represents that 1 bit is used for your sign and 11 bits used for your exponential purpose, that is minus 1 is sign, and you are having the 1 dot, your fraction part. This fraction part use 52 bits, that is multiplied with 2 to the power of your exponent. This exponent uses 11 bits, the standard format of that. So from here, the special values of this exponent in this IEEE standard format encoding is the exponent and the fractions are reserved to represent some special cases, like if the exponent is 0 and the fraction is 0, that means the value is 0. That is, it may be minus n of sign bit multiplied with 1 dot, your fraction is 0 and 2 to the power of exponent is 0. So that will give the value of 0. Multiplied with anything which is multiplied with this one is 0. And if any number, if any exponent, we are writing in the binary form as all ones are there. Okay. So these are binary representation one. That is infinity. The value is infinity. So 0 and infinity. They are the special cases. Another one is if exponent is 0 and fraction is not 0, that means there is a denormalized, the value will be there. That is what we have seen, like 423.4345. It is not normalized because the dot is somewhere inside the number. So no leading one before the binary. So in terms of binary, it will be looks like 111.110.111 like that. So it is not normalized. To make this normalized, you must shift this dot to the very first position after your first binary one digit. And if a exponent is all ones and your fraction is not zeros, then this is not a number. That is not a number. So let us see this example for how to encode a number. This is also important for your assignment. For a given, the real number or float number, and encode this number with the floating point representation. Floating point representation. So this is 1259.123. It is a decimal number. Represent this decimal number into binary floating point encoding. So first what we need to do, we need to convert this binary decimal number into the binary form. So to do that, we take the integer part separately. This is integer portion, this is the fractional portion. So integer will be converted into binary by doing the binary division operation. So 1259 divided by your 2, the quotient is 629, remainder is 1. So if you keep on going those operation, you will find the reminders. When you find this reminder, for integers, we arrange all these reminder bits in a reverse order, so that will give you the binary value as 10011011011. So then to convert this fractional part, as we saw how to convert the fractional decimal into your binary, we do the multiplication operation here. So 0.125 multiplied with 2, so it will give the result as 0.2, and from there we pick the integer bit. The integer bit is 0. From here it becomes 0. And when this result is again multiplied with 2, it will give 0.500. From here the integer part is 2. And when it is fraction part is again multiplied with this 2, then it will give 1.0. So the integer part is 1. So you arrange this fraction, when you are converting this fraction part into binary, you arrange these bits in a same order. So that is 001. So once you combine this and your integer part and fraction part, that gives the binary equivalent. Now this binary equivalent is converted into, in this it must be normalized, because it is a unnormalized the part, as we said, it is a denormalized number because your floating point is somewhere inside. So it must be normalized first. So to normalize this one, this dot will be shifted to normalize this before this one digit. So when it shifts, it is moving 10 locations. So then you can normalize it by moving this. You can represent this normalization as that multiplied with 2 to the power of your 10. So when this decimal real number, the float decimal number or real number is converted into your binary, then you can do the encoding by following the IEEE 754 32-bit representation. So that says that 32-bit representation says that this number should be equivalent to this formula, that is 1.f, and that is multiplied with 2 to the power of f. So for single precision, are converting into your 32-bit. For single precision, as we said, the maximum range of this is your 127. So it will be written as 2 to the power of exponent minus your 127. So this we call the bias. Okay, this you call the bias or the base one. So based on that, the conversion will be done. So from when you started comparing this, then this part is your fraction part that is equivalent to this. Then this part is equivalent to your 2 to the power of exponential link. So 2 to the power of e minus 127 is equivalent to your 2 to the power of 10 in this case. So then when 2 goes cancel, you will get the e minus 127 is equivalent to your 10. So e is equal to 10 plus 127, that is 137 in decimal. When you convert this decimal into your the binary format, then it will equivalent to 1000 1000. So then, once you have the exponent, once you have the fraction, and you have this number is a, the positive number, so sign is 0. So to represent this real number in 32-bit floating point encoding representation is the encoded floating result is sign bit is 0 because it is positive, and exponential one is 100, the 8 bits, and your fractional part is this, so that you will write here, but it requires 23 bits, so all the remaining bits will be filled with the zeros, so this is the floating point encoding with 32 bits, because we are following the precision of your 127 is one example, right? Is this example is clear? Can anyone respond in the chat box? Okay, thank you. Yeah. So similarly, let us take another example for negative number. The signed real number, we call the signed real number. Here we are finding minus, that means it is representing a negative number. But the process is same. What we'll do, we'll first take it is 1.75 multiplied with 10 to the power of 15. So it is a very big number now. So to convert this very big number into your real binary encoding with 32 bits, what we'll do, we'll try this portion first. So in this, you have the integer portion and you have the fractional portion. This is fractional portion, this is your integer portion. Now convert this integer portion into your binary. So you will get, so 1 divided by 2, quotient is 0, remainder is 1. Right? So that is equivalent to your decimal 1 equivalent to your binary 1. And for 75, when you do this multiplication, because it is a fractional value, so you will get 1 1. So the fractional decimal value equivalent to your fractional binary as 1 1. So when you write it, the 1.11, that binary equivalent of this number, and negative side is as it is. Then we need to convert this 10 to the power of 15 into your radius of your binary. You need to convert this into binary. So that is, you need to convert this 10 to the power of 15, because this dot is 15 dots away from this number. So if this 15 is taken, means you have some 15 numbers here. So you simply convert this 10 to the power of 15 into your binary, so that the entire decimal become your binary form. So how to do that? 10 to the power of 15 is equal to 2 to the power of some x. Let us assume x. We need to compute x. So to compute that one, apply the log algorithm on both the sides. So log 10 to the power of 15 is equal to your log 2 to the power of x. So after that, to find out this x value, you can do the division operation of your logarithm to simplify this equation. So log 2 divided by log 2, do the division operation on both the side with log 2. So you will get x is equal to 15 log 10 divided by your log 2. So log 10 value is equal to 1 and log 2 value is equal to 0.3. So when you simplify this, 15 multiplied with your, multiply with 10. If you remove this dot, it become inverse. So it is 10th position. So 10 divided by 3. So when you do this, 3 divided with 5 times. So 5 times multiplied with 10, it will give 50. So the 10 to the power of 15 is equal to 2 to the power of x value is 50. So 2 to the power of 50. So you can replace this 10 to the power of 15 with the 2 to the power of 50. So this is the binary conversion. Now, it is a signed binary number. It is a signed binary number because one is, minus is there. So from this, this is sign, this is 1 dot, you are having fraction multiplied with 2 to the power of x. So when you compare that with this number, you need, if fraction part is 1, 1, your exponent part, that is 2 to the power of e minus 127 is equal to 2 to the power of 50. So when 2 goes cancel, you will get the e minus 127 equal to 50. So that is e is equal to 50 plus 127, that is your 177 in decimal. Its equivalent binary is 100. So now this is your exponent part. This negative represented with 1 and your fractional part is 1, 1. So total it is 23 bits. So all the remaining 21 bits are filled with the zeros. So this is the encoded float result of a given number, for any signed number, negative number. Is this clear example? Thank you. Thank you. Okay. So we'll see another example. Suppose, we have, I'm covering 3 different types of example here. One is a signed positive number. Second one is in terms of very big number with negative value. Third, we cover that very big value in a fraction minus 1, 10 to the power of minus 1. So let us see, this is a signed number. So minus 10 to the power of minus 1 is your dot is moved. After that, you will have your dot is moved minus 6 positions on right side. That's why it is minus 1. If it is positive 1 means your dot is moved, in the previous example, like 15 positions from its current position to that. That's why we written as 10 to the power of 15. Here 10 to the power of 6 means this dot is moved in 6 positions. 1, 2, 3, 4, 5, 6 position like that. So how to do that? So now we have this number. This is integer part and this one is your fraction part. Now integer is converted into binary in the same way, 32 divided by 5, and we follow that every quotient is repeated so that we get the reminders raised. So these reminders arranged in a reverse order. So 1 0 0 0 1 1. So that is the binary value, the decimal value of 31 is equivalent to the binary value of this string. So similarly, we do for 5, it is a fractional part, so that is multiplied with 2. So we'll get the result 1 0, and from here the integer bit is 1. So the fractional decimal value of this is equivalent to the fractional binary value. Then when we club this and this together, it will give this 35.5 number. Now we have 10 to the power of minus 6. We need to identify, we need to convert this into its binary equivalent. So in binary equivalent, do the same procedure. 10 to the power of minus 6 is equal to your 2 to the power of x. Suppose we need to compute x. So apply the logarithmic algorithm on both the side. So you will get the x log, when you convert this into here, then you will find the x log 2, that divided by log 2 divided by the log 2. So on both the side, you will get the log will be cancelled here. Your log 10 is equal to 1, log 2 is equal to your 0.3. So that will be multiplied with your minus 6. This number is minus 6. So when you compute that minus 6, so you will get when it is converted into 3, then it becomes 10, become inverse there. So 3 ones are 3 twos are. So here minus symbol is there. So minus 2 multiplied with 10, it is minus 20. So therefore, 10 to the power of minus 6 is equivalent to 2 to the power of minus 20. So when you write that, this, when you convert this into binary, you will get the fractional part, binary representation of 35.5 multiplied by, decimal is converted into binary as 2 to the power of minus 2, minus 20. But here dot is here, it is not normalized number, it is denormalized. To normalize this, you move this number from, move this binary point, this binary point to this location as 1, 2, 3, 4, 5, 6 position, the 5 positions. So you will add, it is moving right side, I mean the left side, so it is a positive exponent one. So you will get plus 5. So when simplifying this, you will get this number as 2 to the power of minus 5. So this is your binary equivalent of your decimal real number. Then you start encoding this with 32-bit representation. So to start encoding, you compare this. This is your f, assume that f. So this is your fractional value, f, and this is equivalent to your 2 to the power of e minus 7 is equal to 2 to the power of minus 15. So when you simplify this one, then simplify this one, you will get this 112, 112. So you will get the binary value of this. So when you converting it, it is a positive number. So the sign bit is 0, and the exponential part is this, and your fractional part is this, and all the remaining bits will be represented with 0. So this is the 32-bit real number encoding procedure. Somebody asked that you can explain the E minus, as we said, for single precision. The single precision, according to IEEE 754, it takes E minus 127 as bias. If it is a double precision, precision, then its range will be changed from, if you recall this slide, somebody asked this question, let me clear them. Okay. When you see this range of that, when you're finding this range of this, you are getting for the single precision and double precision range, you're finding this range here, almost, this is 2 to the power of minus 7, it is the exponential part. For double precision, it will be changed to 1028. So that's why, to make this the range for the maximum positive float number in 32-bit, it takes single precision, that is 127. So it writes as 2 to the power of any exponent position, whether it is moving left or right, that will be subtracted from 127. And now somebody is asking how it is become 15. So that is, here we call that, because when we are doing the normalization of this dot point to here, it is moving 5 positions to left, positive side. So that's why you will add 2 to the power of 5 positions of your exponent part. So then when you do minus 20 plus your 5 is equal to 2 to the power of 15. Is it clear, Molano? Okay, so this is, these are 3 different, the examples of encoding any float numbers. So based on this, you will get the assignment by tonight. I will announce the assignment so that it will helpful to you. Okay. So the floating point computation. So there are standard algorithms for this floating point computation, that converting that binary between the binary float to your decimal floats, or decimal float to binary float. This is just what we do observe. So doing the Same thing for your sum, subtraction, the multiplication and division. I will not cover these algorithms, but you can easily find these algorithms online in the or in the textbook. Okay, so in the next class, we'll try to discuss this basic ALU design, and then we talk about the performance. So I would like to stop this session here. If you have any questions, you can, they ask me.